to Chapter 1, About Science. This is Chapter 1 from Conceptual Physics, 12th edition by Hewitt. In this chapter, we're going to introduce science in general and physics in particular. All right, here we have the table of contents of some general topics we're going to cover. Nothing specific, just some big, broad ideas. When I go through these lecture slides, I'm going to go through at a pretty fast rate, not getting into the details, but just calling attention to some things that that I feel you should pay attention to. Okay? So here we have a definition of science, mentioning that it's ongoing and is a body of knowledge. We also have a quote from Lord Kelvin. Basically, the idea of this quote and the reason the author decided to include it is because it's really calling attention to the idea that if you can quantify something, you understand it better, right? So it's kind of like, oh, you can think about, oh, this is how much I weigh, but if you have a number, then you can say track your weight, just as one example. And so that there's so many ways that quantifying gives you a deeper understanding of the things around you. All right. And that leads us to the idea of measurement, right? Very basic idea here. This allows us to relate how much you know about something. Okay? For example, a pinhole image of the sun can nicely lead to a calculation of the sun's diameter. All right? In fact, I won't solve the problem here or anything, but I do want to call attention to this because I think it's kind of a good example of the level of math that we'll be doing occasionally in this course. All right? So if you take a look at this here, we have someone that's holding a piece of paper, holding a piece of paper a height h above the ground. And if you look at this box here, the equation that I boxed off, we see that this is a known distance, something you would know from a previous measurement. That's the distance from Earth to the sun, okay? 150 million kilometers. And if you know h, of course, right, you can measure h, then you can come up with this ratio of 1 over 110. And in doing so, then you can solve, you'd also know d, because you can easily measure little d, that is, right there, little d, you could easily measure with a measuring tape. You can then solve for big D. Because you think about it, this is an algebraic expression in the first box I drew, right, this one here. And the only unknown is big D, uppercase D, okay? So that's the type of equation that you could set up and solve for in a class like this. In fact, the idea of pinholes, right, shows up in the holes between leaves, right? This is the pattern that you would normally see on a sunny day because the light is shining through the gaps between the leaves and making a sort of a magnified version of those gaps, okay, based on how high above the canopy is above the sidewalk. But on a solar eclipse, or particularly a partial solar eclipse, well, all of the little spots, the pinholes, become crescents. Right? And it really goes to show that light is coming from a circular source in most cases, but if it comes from a crescent-shaped source like this, then the source of the pinhole projections changes. The shape of them changes. Right? So fascinating, and that's something that you wouldn't necessarily think about because we take a lot of science for granted, right? We take a lot of measurements and observations. It's just the way things are. But we, of course, can ask that question, why are they that way? And maybe this is something you observed firsthand when we had the Great American solar eclipse that passed over in, I want to say 2018, and I know we have another one coming up in 2024. All right. So moving right along, here's a famous measurement. This is one I particularly like. I will sometimes assign this as a homework problem in the class. This is a Eratosthenes measurement where this Greek philosopher and early scientist was able to estimate the diameter of the Earth, as you can see here. And so unlike in the European Dark Ages, at the time of ancient Greece, so this is over 2,000 years ago, we had an idea, a speculation that the Earth was indeed round, based on things like the idea that you see, the curvature of the Earth when you're in the open water and so on. And so that was the assumption of Eratosthenes, and he set up an experiment where he measured the length of a shadow at one particular location at the city of Alexandria along the Nile in Egypt, because Egypt was part of the kind of the Greek diaspora. And then in a city south, another big merchant hub south of Alexandria was the city of Syene, which was a known distance down the Nile. And there was a vertical well, and they were able to find out when the sun was directly overhead, and with some simple geometry, able to get the angle of 7.1 degrees, and then calculate the circumference and thus the diameter of the planet. Because the relationship of pi, which of course relates the diameter of a circle to its circumference, was well known to these Greek scientists and mathematicians. Okay, So very interesting experiment and measurement. Similarly, a very early scientist, Aristarchus, was able to estimate the distance and size of the moon based on solar eclipses and lunar eclipses. So using both types of eclipses and measurements made during both, and I won't get into the details, the amazing measurement of both the orbital distance of the moon's approximately circular orbit and the actual size of the moon itself, its diameter, was able to be estimated to pretty good accuracy. Right? Quite astounding. All right. So, mathematics, the language of science. Integration of science and mathematics occurred some 4 centuries ago. Okay, so this idea of using symbology, what we think of as an algebra class, what we think of as any math class where we use x and y and use plus symbols and minus symbols and division symbols. That whole idea of having that really be the backbone of mathematics, but also science, is much newer than Aristarchus and Erasmenes. Their approach to using numbers was done in sort of an essay format, right? A written format. There was not this idea of condensing things down to equations. That came around the 15th century, okay, 15th, 16th century, all right? Ideas of science are unambiguous when expressed in mathematical terms, right? And that obviously big turning point. You can think of the entire European Renaissance, but of course all these ideas would have been percolating much earlier worldwide, and you cannot exclude the importance of the Arabian world in terms of kind of really laying the foundation and preserving many of the mathematical ideas for centuries, right, from the Greeks up to the European Renaissance. Right? But we're not a history class, so we'll leave some of those details aside. Equations of science provide expressions of relationships between concepts, and they're guides to thinking. And sometimes you hear about the scientific method. There's no one scientific method, and sometimes that allows people to kind of make fun of the scientific method because it's really, it's kind of like, okay, yeah, there are hypotheses and you want to propose one, but sometimes there's observation. You might not start with a hypothesis. You might instead start with an observation. The hypothesis might come later after you've collected data. Right, so you don't always start with a hypothesis. It's not rigid, and it's not necessarily one loop where you test the hypothesis and you go back and adjust it. Sometimes things go around many times, many attempts at changing hypotheses. Maybe a full theory is never formed. Maybe a theory comes very quickly. But there is a definite difference between a hypothesis and a theory. Okay. So here are the common steps. Again, not rigid but common steps. Recognize a question. All right, a puzzle. And then make a hypothesis, okay? You don't necessarily have to, but this is a good opportunity to make an educated guess. Predict the consequences of the hypothesis because your hypothesis must be testable. If your hypothesis is not testable, well, maybe it could be testable in the future, so in that case, it's kind of a hypothesis waiting to come. But if it's never going to be testable, because maybe its very nature is that it's based on untestable, unknowable things, well, then actually that's not scientific. So if I say there are unknowable particles inside of my body, well, that's not a scientific hypothesis because they're unknowable. They can never be tested. Okay. Mysterious ghosts live in my walls. Well, you can never test that, right? Because they are quote unquote mysterious. Then you're going to perform experiments. Those are the tests that I mentioned. Then you're going to formulate the most simplest general rule. Okay, that will become your theory. The simplest idea, the one that is the simplest explanation that directly relates to the evidence that you collected in support of your hypothesis. All right? The attitude, right? This is not the scientific method, but instead the scientific attitude is one of inquiry, experimentation, and willingness to admit error, right? Because things can be wrong, and they cannot appear wrong until decades later, right? Something can appear so right and work so well, and maybe there's just one kind of loose end and you think you're going to clean it up and it's just going to be one little thing that requires like a little experiment because maybe it's just a little bit of error, but it turns out that little bit of error is actually a fundamental mistake in your theory. Think about theories that change the world, like the theories of Einstein, which we'll mention in this class, right? Those could have just been written off as small errors in measurements, but it turned out that they were fundamental changes to the universe and to our understanding of it, okay? Of course, the universe was always that way, but we didn't realize it was. So scientists are experts at changing their minds, okay? They have to be able to admit they're wrong, and they have to also be able to admit they're wrong in a culture that doesn't like the people to admit they're wrong, right? It's something, because if you admit you're wrong, if you made a mistake, then you can't trust somebody that makes mistakes, right? Well, that means you can never trust a scientist. But I think you can trust scientists because it is okay to be wrong. It is okay because you have to then be able to repeat the process, go back, always base your ideas off the evidence, okay? But if there's new evidence, that means new ideas. All right? You have to accept those experimental findings. A fact is a close agreement by competent observers who make a series of observations about the same phenomenon, okay? But facts can change, right? A fact is not unchangeable. It is just, it's like a theory. It's just based on the evidence, okay? But if there's new evidence, that by its very nature is a new fact, okay? Facts are not unchangeable. A scientific hypothesis and an educated guess, okay? That's part of that method that we mentioned before. All right, so which of these is a scientific hypothesis? All right, so whenever these questions come up in these lecture videos, you absolutely should take an opportunity, pause the video, and make sure you're confident about the answer. All right, take a look at the options. All right, so they were all scientific hypotheses, okay? All of these meet the criteria. They are all testable, educated guesses. All right. Which of these is not a scientific hypothesis? Think about what I said before. All right. Undetectable particles, because by their very nature, they're undetectable. That means you can, well, never test for them, right? Okay. That's not science. Okay. So some ideas, some key terms that fall into the scientific attitude. All right. A law or principle is a hypothesis that has been tested repeatedly and has not been contradicted. Okay. So that's an interesting thing. So a law, like the law of gravity, isn't a theory because it's just one single observation, right? So it's just saying, okay, well, this is an observation, this is the way it works. Well, that's actually just an educated guess. But it's so fundamental that there's nothing, and it's never been proven to be wrong, that it becomes a law. So laws are interesting. They're almost like short circuits between the hypothesis theory process. And they're usually very concise, very direct observations, like gravity, like movement of objects, like Newton's laws, okay? Which we'll, of course, talk about in some detail. A theory is much larger. It's a synthesis of a large body of information. And it pertains to more complex ideas, like the theory of evolution in biology, of course, which has many physical aspects to it. The theory of relativity by Einstein, right, which is this big body of observations and big theory built on many building blocks, right, many pillars of a foundation, okay? So which of these often changes over time with further study? Okay, think about what I said. What's the best answer? Of course, both of them, right? Facts and theories can change. All right? A person who says that's only a theory likely doesn't know that a scientific theory is, right? If you're paying attention, you know the answer to this one. Make sure, right? It's a good opportunity to just kind of wake up, pay attention, all right? It, of course, is D, a vast synthesis of well-tested hypotheses and facts. All right? So what about comparing science to art and religion, right? Because all these things exist in the human endeavor. They're all wonderful parts of what it means to be alive and a human, okay? So science is of the natural order and involves the discovery and recording of natural phenomena, right? It has huge benefits to the world, right? Following the scientific method, understanding natural phenomena can lead to the modern world where we have computers, we can go into space, right? All of this is thanks to science. But science isn't everything, right? Art is the interpretation and expression of the human experience, right? You can't just live in a world that only has facts and observations. You want to be able to kind of like talk about how your particular mind processes that, right? Art is very individualized in a way that science is not. And then religion involves faith and worship of a supreme being, right? Or supreme beings. And that, that's its own thing, right? That's so important to so many people to have that idea of religion and maybe combine that with art. And you can be a scientist and be religious. All right? So similarities between art and in science. Knowledge of what is possible in human experience and in nature, and knowledge of both affects our views and decisions about the world. Absolutely. Similarities between religion and science. Both deal with unanswered questions, okay? And there are some questions that are so fundamental that science likely won't have an answer to them. Like what existed before the Big Bang? Where did the Big Bang come from, right? The incredible amount of energy that created all of the cosmos and created space and time itself as far as we know, right? Well, science may never have an answer to that question, so maybe religion is a good place to look for it. You can just kind of have your own belief. And if a group of other people believe it, then That's perfectly fine for a social structure, is it not? Okay? So between a pilot and a priest, who do you think should fly a commercial jet airplane? Who should perform a marriage? All right? Silly question. The pilot should fly and the priest should perform a marriage, right? So people have their roles to play. In other words, we're not trying to step on any toes here. Okay? So science is concerned with gathering and organizing knowledge. Technology, on the other hand, is the use of scientific knowledge for practical purposes and to provide tools for further exploration. Okay? So that's when you hear about STEM, right? Science and technology, engineering and mathematics. Well, technology is applied science. Okay? Engineering is also applied science. Physical sciences include geology, astronomy, chemistry, and physics. All right? So that's what is known as the physical sciences. Life sciences include biology, zoology, and botany. So physics underlies all the sciences, and sometimes that means that biologists or other scientists will be like, hey, physicists act like know-it-alls. But physics is the most fundamental science. Everything involves the movement of particles, right? Cells are made up of particles. Physics is absolutely well equipped to study the movement of the most fundamental building blocks of matter, these particles I mentioned. And since the particles exist in chemistry, they exist in biology, everything, in that sense, physics will apply to all. Now, can you take the basic ideas of, that we'll talk about, conservation of energy, conservation of momentum, Newton's laws, and apply them to understanding biology? No, because the systems are so complex. There are so many trillions of moving parts that it would not make sense, at least, kind of with our current way that we process data, to take a purely physical approach to very complex things, even chemical systems. So, in that sense, the other sciences absolutely have a role to play. They're well equipped. But physics is the most fundamental, all right? And we'll go on to say that. So although physics may be the most difficult science course in certain schools, right? I've certainly had experience with that myself. When compared with the fields of chemistry, biology, geology, and astronomy, it is the simplest. It has the fewest equations. It has the simplest equations, right? Because it's very, very, at least pure physics is very rarely or almost never making approximations. It's just based on a few fundamental laws, all right? And that is it for lecture 1. Thank you so much for checking out this video. There will be future video lectures for all of the chapters.